from the University of Antwerpen at the Center of Healthcare Technology, where we look at different applications within the broad field of healthcare. And one of the problems that occurs often in hospitals is that there is a significant amount of oxygen lost at the valves inside of the rooms where the patients are. These valves, they have some small leaks, and it costs the hospital a lot of money. So one of the problems we were contacted for is, can you detect air leaks using ultrasound? And we do a lot of work around in-air sonar systems using ultrasound. So we had the material lying around to do some experiments around this problem. So we know that air leaks, they produce ultrasonic emissions that's caused by the turbulences. When you have a small leak, the air goes out, you get some effects there in the air, and you get some ultrasonic emissions. And using a microphone array and some signal processing techniques, you can detect those air leaks. There has been a lot of work previously. But we wanted to look at, can we increase the selectivity and the spatial accuracy of the system using some inverse techniques. So this is the sensor array that I'm talking about. So it's a random array of microphones. They are MEMS microphones. It's about 8 by 5 centimeters. I have a prototype with me, so afterwards, if you want to see it in your hands, you can come to me. I have it. And so you have in this case, it's 32 microphones. And we define a coordinate system with an azimuth angle, so the angle in the horizontal plane, and the elevation angle, which is the phi angle depicted in the picture. So the microphones that we use, they have a broad frequency response. We use them in the ultrasonic range between 25 and 100 kilohertz approximately. So why do we use a random array? If you would use a dense array, where the microphones are spaced half the maximum wavelength, the minimum wavelength, the half of it, when that's the maximum spacing, then you have sampled your incoming wave field according to the Nyquist criterion, and you don't get any ambiguities. But you see that the point spread function is really wide. So you have a really wide main lobe, and you have some side lobes there. And you see that especially at 20 kilohertz, you have a really flat response spatially. So the small balls you see, it's basically the frontal hemisphere, the spatial filter that you have with your microphone array in the frontal hemisphere squashed onto the surface of the projection. So, and also if you look at the energy, you see that you get a really broad response. So let's say we make the array bigger and we don't care too much about this Nyquist sampling. You get a problem that there is regularity in the array and you get grating lobes. And also in the energy, you get the grating lobes. And this means that it's the same effect that you get in when you try to estimate the frequency of a time series. If you undersample it, you get also aliasing. So when you randomize the array, you get also grating lobes in each individual frequency, but they don't move spatially in a regular pattern because the array is random. So if you look at the energy, so if you integrate over the complete frequency band, you get one main lobe with a continuous level of side lobes, basically. That's what you see at the bottom here. So for the dense array, you get a nice response, but it's really broad and it doesn't go too deep. When you have a regular array, but which is too big, so where you undersample the wave field, you get grating lobes. And with a random array, you get a really nice response. This is an approach we have used for both active sonar sensing, where you emit a signal and you listen for the echoes and you try to localize them. We have done this with this random array, and now also for the air leak detection. And the beamforming approach we use, or we choose deliberately to use, is a really data-independent beamformer, just delay and sum beamforming, because it's very robust against all types of calibration errors. The only problem with this type of beamformer, or one of the problems, is that the spatial resolution that you can get with your array is dictated by the aperture alone. You don't care how long you measure, you won't get any better localization results. So there's different other types of beamformers presented in the past, and it's like the Capon beamformer or music beamforming, or they're actually type of beamformers that are data dependent. So you take your incoming data, you do some stuff with this data, you adjust the weights of the array according to the incoming data, and then you get better spatial accuracy. But often they're not really stable. When there are correlated signals, or there's a whole lot of different problems with these beamformers, and that's why we don't choose them, because if you have some mismatch in the microphones or stuff, it doesn't really work really well. So what we propose is that you make your acoustic image using this classic beamformer, and then you use a sparse representation inspired method like compressed sensing to decompose this image into its atoms, into its individual reflectors. So how does it work? You have this random microphone array, and you make your acoustic image. So on the x-axis is the azimuth angle, on the y-axis the elevation angle. It should not be square. It's basically on a sphere, but for easier visualization, I just made it flat. And so you make this acoustic image E with a direction vector psi, and psi is the combination of the azimuth and the elevation angle. And so you have 5 leaks. They're spaced in a particular pattern, and you get this acoustic image. And what you want to do now, in this case it's really easy because you can visually see that there are 5, but you want to estimate the locations of these sources. So how do we do that? We introduce 2 assumptions. We say that the image can actually be written as a sum of the acoustic images which would occur if there was only one source present. So if you have these 5 sources and you have one source, you make the image, you have the other source, you make the image, you can sum them. That's the image that you see there. That's an assumption, but we checked that assumption and it works really well because the signal processing is mostly linear that we use, and then you can use this linear assumption. And also that we have a sparse environment, so that we don't have too much sources simultaneously present in the environment. So it's not when you have 30 microphones that you have 30 sources at the same time, but that won't happen often as well. Mostly in hospitals there are 3 valves, for example, and then the problem is sparse, or can be considered sparse. So the next step is that we calculate the point spread function of the imaging system, like point spread function you have in an optical imaging system. But in this case, the point spread function is direction dependent. An object straight in front of you will have a different point spread function than an object located to the above left, because the effective aperture of the array changes when you come from a different direction that's not head-on. So that's important that you calculate the point spread function for every direction that you're interested in. And then what we do is we try to write the measured acoustic image. So the acoustic image in the first square is a measured one, and we try to recreate that image using a weighted sum of the point spread functions. And we try to find that weighted sum of the point spread functions in a least square sense. That's where you see the d times x. D is the dictionary containing all these point spread functions. X is the vector that we want to estimate with the positions of the air leaks and the strength of the air leaks. And we try to find it in a least square sense, but we regularize the problem using an L1 regularization where we enforce sparsity onto the vector x. And so if you do that, you can find the reconstructed acoustic image. And what you often see is that you find more sources than are actually present, but they're often clustered around the true positions. We'll see that in the experimental results. So in the first case, we have 5 air leaks. They're spaced a bit arbitrarily. And when we try to decompose it using this sparse technique, you can get the multiple sources, but often they're a bit clustered around the true positions. And that's caused because, one, this linear assumption is not 100% correct. So the sparse reconstruction algorithm tries to compensate some of the errors by adding additional sources. And second is that the point spread functions are not 100% completely accurate. So that's also an additional reason why there are some additional sources there. But all the time they're clustered around the true source position, so it's not really a problem. And then actually the main application for this is when you have a really strong leak and a really weak leak closely spaced to each other. That's the biggest problem why you would do something like this. Because in this case, it's really visually that you have these 5 sources. But in this case, you have a really strong source, and the side lobes of this strong source, they overshadow the main lobe of this weaker source. You can visually see, so there's these two dots in figure A. So that's the position of the two sources. And using this sparse reconstruction technique, we can also find these two sources. So visually, it's not really clear to see it. Also, when you plot it on a logarithmic scale or something, it's not there because the side lobe of the strong source overshadows the main lobe of the weak one. So it's not really clear to see. But using the sparse technique, because you enforce the sparsity and it tries to reconstruct the numerical values in the image, you're able to detect those. On a closely related topic, like I hinted before, we also work in an active sonar sensing. And there, the point spread function has this extra degree of freedom, namely the range. You emit a pulse, you wait for the echoes, you measure the range, and also you measure with the same array the angle of arrival, and then you have this acoustic image consisting of 3 dimensions, the range, and then the direction. We have applied this similar technique on that problem as well. And there, the application is much more clear. If you want to drive with a robot through the door, you get a really strong reflection from the wall, but you won't get the weak reflection from the side of the door, for example. And there, this technique would be very useful. We have a poster this afternoon in a poster session explaining this problem in more detail. So if you want to come there, you're really welcome. I would explain it. So to conclude, we have developed or we have applied sparse decomposition algorithms on acoustic images to increase the spatial accuracy of the system. So we don't choose for the classic inverse or data-dependent beamforming techniques, but we use a really basic beamformer and then try to improve the accuracy using a sparse decomposition. And more really important is that strong and weak sources that are really close by can be distinguished simultaneously. This method it's an inverse method, so it doesn't work all the time. There can be problems with it, and it works well as long as this linear superposition of the point spread functions that it holds, and it seems to hold in many cases. Then the number of leaks is small, so that we have a sparsity effect going on, and then that the dictionary contains good point spread functions. So it's important that you put the right stuff in there for the algorithm to build this acoustic image. And in the future work, we want to optimize the strategy where we sample this acoustic image in a measurement phase, because like in compressed sensing, you can randomly subsample it again. So again, there you don't choose, don't have to build this full image. As long as you make the solution sparse, you can just choose some directions randomly, build your acoustic image with that, and then still find the accurate source positions. So that's something that we will do in the future, because that makes the algorithm computationally much, much more efficient. Thank you.